Hello everyone, and welcome to this Copernicus Marine Training Marine Data for Arctic. I'm Alexandre Embrun from Noveltis, and I will be your trainer for this workshop. So for this Jupyter Notebook, the topic is Arctic sea ice. So as you may suspect, it's a critical component of the Earth climate system. And recent observations have shown that the extent of the Arctic sea ice is declining over the years, especially in summer, which is the time of the year where the sea ice reaches its minimum surface. So this has several implications. First of all, this disturbs the oceanic current circulation. This also creates a negative retroactive loop because the Arctic sea ice tends to reflect the light of the sun a lot, and as there is less and less sea ice, it reflects less and less the light of the sun, which cancels the cooling effect that it used to have, and therefore exacerbates this declining phenomenon. So those two examples show why it is crucial to understand how Arctic sea ice evolves and what are its impacts on other parameters. And this is what we are going to study in this notebook using a model product from the Copernicus Marine Service catalog. So for this training, this is a Jupyter Notebook, so we'll be using Python. So here's a brief presentation of the required Python modules that you will need for this training. So we'll use NumPy, which you should be already familiar if you're already using Python. So it's great to compute scientific arrays and managing tables. Pandas is also very useful to manage tables. Xarray is the most commonly used Python library to open NetCDF data, which is the format of most scientific products, especially with the Copernicus Marine Service catalog. So SciPy is a library used for scientific computation and statistical computation. We'll be using this to derive trends from the data. And then Matplotlib and Cartopy are used to plot. So Cartopy is used for the maps and Matplotlib for all the other types of graphs, and it's also a very commonly used library in Python for visualizing data. So all these libraries should be installed within the Copernicus Marine Service Python kernel, which you can select here. So make sure you have the version number 4. Because it will contain all these libraries that you need. So we'll just execute this cell to make sure all the libraries are loaded. And now we're going to present you the product that we're going to use in this training. So we'll use only one. It's a reanalysis. So it's focused on the Arctic Ocean and proposes a lot of physical parameters. In our case, we will be using the sea ice concentration parameter and the seawater potential temperature parameter. But of course, if you want to know more, don't hesitate to visit the dedicated Copernicus Marine Service page, which is here. You have all the other variables that you can select from this dataset. And so this reanalysis is interesting to us because it covers a very large period of time, so from 1991 to 2023, which is interesting to us because usually when we study trends in climate data or other environmental parameters, it is most of the time useful to have several decades of data because this time scale is where trends become significant. So in our case, as we will be dealing with data over 3 decades, we will only need to use monthly data. as a compromise. So as you can see, the dataset proposes daily, monthly, and yearly sampling of the data. So monthly is a good compromise between having details in the data and needing less space to process and store all of it. So monthly is a great compromise. Here are the link to the product user manual and the quality information documents of the product if you want to look deeper into how the product is built and used. So now a brief point about how to access the data. So with the Copernicus Marine Service, there is a recent toolbox that you can use to retrieve the data that you need. So you can take a look at the dedicated article to have the tutorial on how to use it. I will quickly show you how it's done here. So basically, you just have to import this library, which is specially developed for this. Make sure, once again, to have the Copernicus Marine Service version 4 kernel developed, because it's only available in this kernel. So you import this library, and then you use only the subset function from this library. So basically, you just have to make sure you have all the different parameters that you need to subset your dataset. So here you have the ID of the dataset that we are using, our product. Here you have the names of the variable that we're going to retrieve. Here, those are the area of interest that we are retrieving data for. The date range that we want to have. So as you can see, we are requesting for 3 decades of data. And here are the depth level of data, because we are using oceanic, an oceanic product, so there is also a depth dimension. So we only shooting a small range of depth. And here is the output information to retrieve the data. So in order to find all the parameters, especially the dataset ID, so you can just go to the dedicated pages of the product, click on Data Access, and here you'll find the information you need. So as example, I'm just going. So I've already downloaded the data here, but I'm going to do it again just to show you. So it will ask you for your credentials. And as you can see, it will look in the catalog how if your request is valid and where the corresponding data is located. So apparently it's found the data I've requested. It asks me to confirm whether I want to download it or not. Just type Y for yes. And the downloading is starting, as you can see. So it's just a duplicate of the dataset that I've already downloaded, but you should have this one. Here this is the same operation, so I'm not going to do it again, but it's for the temperature data, which we'll be using a little bit later in the training. And once you've executed those 2 cells, you should be all set to complete this notebook, to execute everything. So first of all, we'll take a look at the sea ice dataset. So the first one that we've downloaded. So you use Xarray to open it. And as you can see here, this is our dataset with the 2 variables that we have downloaded. So this is our main variable of interest here, sea ice concentration. So in this interface, you can click on this icon here to have more details about the data, to display the metadata actually. So you can see that this is the sea ice area fraction. So basically it means that it gives a proportion for each pixel. It gives a proportion of the pixel area that is covered with ice. So of course, as it's a fraction, the range of the variable is between 0 and 1. We have other attribute here for the dataset itself. So as you can see, this is the starting date of the dataset, and we have other information about the model that is used, the source data, the institution where it comes from, etc. And here, this is a coordinate system. We have latitude, longitude, and time. So to have to visualize the dataset, you can learn to draw a map with Matplotlib and Cartopy. So there are a few things to prepare before drawing the map. So first of all, you have to define an area of interest. So it can be, of course, the whole world, but in our case, we're only limiting ourselves to high latitudes, because we're studying the Arctic. We have to make sure that the data we want to plot has only 2 dimensions. So here we have 3, because time, latitude, and longitude. So of course we want to plot a 2D map, so we only have to keep latitude and longitude, so we have to find a way to remove this dimension. And to do this, we basically only going to select one date, so which is a simple thing. But for example, you can perform like an average over the time dimension, for example, but we will do simple for this first map. And as we're studying the Arctic, it is much more convenient and visually appealing to work with North Polar Stereo projection. So basically a map projection centered on the North Pole, which is much more convenient than, for instance, a basic 2D flat map. So this is what we're going to do, but as you will see, it takes a little more time for this projection to be plotted, so I may have to pause the recording before executing this cell. So as you can see with the star here, the cell is being executed, but it may take some time. And also note here that to save some time on the plotting of this cell, I've used the coarsen function, which is a way to transform the dataset to a lower resolution. So here I'm dividing the latitude dimension by 5 and the longitude dimension by 10, because that way the dataset becomes lighter and it is easier to plot. And so here is our first map of the Arctic sea ice thickness on the Arctic. So as you can see here, we can clearly see the pixels here because I have coarsened the dataset, but plotting the full dataset will do something a lot smoother. So now we will be working with a sea ice extent. So as I said, the only variable that we have to compute the sea ice extent is the sea ice concentration, which is the fraction of each pixel covered by ice. But it doesn't exactly tell us what is the actual surface covered with ice. I mean in square kilometers. So we're going to calculate that. So to do this, all we have to do is to calculate the surface area of each pixel, which is not necessarily obvious because as we are near the North Pole, the surface area of each pixel decreases with the latitude. I don't know if you can see here, but here we can clearly see the distinction between several pixels. But as you can see, as we move to the center of the highest latitudes, the pixels get narrower and narrower. And here we can't distinguish pixel from one another because they have become very narrow. So the surface area of each pixel decreases, and we have to calculate that based on the projection. So this is what we are doing in this cell. So we're calculating the pixel area for each pixel. So you have to compute the radius of the Earth and the latitude and longitude values. And this is the formula to retrieve the area for each pixel. And once we've executed this cell, we are storing this result in a new variable, which is here. So we have the pixel area in square meters, I think. Yes. for each pixel. And now all we have to do is to multiply for each pixel its area with the fraction that is covered by ice. And we have the sea ice extent in square meters, and if we convert it in square kilometers. So this is what we're doing here, computing the sea ice extent. Okay. Now we are ready to visualize the trends in the evolution of the sea ice extent in the Arctic. So to do this, we are going to resample a dataset to have yearly values, to have its to remove actually the seasonal effect, because as you know, sea ice extent increases during winter and decreases during summer. So we want to erase this effect to have the long-term and large-scale evolutions. So here we resample to have yearly values. And using SciPy and line regress, we perform a linear regression to retrieve the trend of the data, which will be stored in the slope variable. So here are our results. We see that we have a clearly decreasing trend in sea ice extent over the last 30 years, with quite a strong correlation coefficient because it's quite close to -1, and a very low p-value. So in this test, p-value is a result of the hypothesis test, with the null hypothesis being that there is no trend in the data. So this is actually quite significant. And now that we have computed this, we can show it on a graph to show the evolution of the sea ice extent. So here in blue you have the actual values or yearly values that we have just resampled from the dataset, and in green this is the trend line, which is here, and here is the approximate decreasing rate of the sea ice extent, which is approximately 46,000 square kilometers per year. So now to go further, here we have performed the yearly evolution computing every year as a whole. But as you have said before, it is especially during summer that the sea ice decline is the most dramatic. So here we just do like a finer comparison, and we'll be performing the same calculation, this time only selecting the summer and winter. So for winter we're going to do things simple by only selecting February, and for summer we only be selecting August. So February is month number 2 of the year, and August is month number 8 of the year. So we're selecting those months in the dataset and computing the trends, just like we did before on both datasets, so one for winter, one for summer, and plotting the trends. And so you can see that both datasets have decreasing trends. However, the decreasing rate is not the same. Here you can see that the sea ice extent is decreasing by 24,000 square kilometers per year. But during summer, this is a lot more dramatic because it's almost 3 times as fast as in winter, because here is 66,000 square kilometers per year. So there is a clear difference in dynamics of the sea ice evolution between the winter months and summer months. So this is quite a result already, and in the next section we're going to keep looking at the summer values and see how those trends are distributed spatially. So this time we are going to do exactly the same calculation as in here, the trends calculation, but we'll be doing this for every pixel of the dataset. So this is what we are doing here. It may take some time, of course, because we are processing a lot of data all at once. Note that here we will be using only the sea ice concentration parameter, so the fraction area of each pixel covered by ice, because it is more convenient for studying pixel by pixel. We needed the sea ice extent in square kilometers to have the total surface of the Arctic sea ice, but this is not exactly what we're studying here. So for this trend analysis, we'll only be using sea ice concentration, and you will see that it is well, in this context, easier to understand. So the cell has finished executing, and now we'll be plotting this on a map and see what the results are. Okay, so it's also taken some time to execute, but now it's finished. So this is our result. So as you can see, those are the trend for each pixel with the sea ice concentration trend evolution in % per decade. So as you can see, there are several areas, especially in the outer perimeter of the North Pole, where the sea ice is really decreasing, especially around those islands. So the Severnaria, Zemlya, and Honshu archipelagos. And there are also a very small area here where there seems to be an increase in sea ice concentration around Greenland and Svalbard. But well, in most cases, especially in those few areas, well, the decreasing goes up to minus 30% per decade, which is also quite a lot. So now in the next section, we'll start to use temperature data. So of course we know that temperature is one of the main, if not the main driver of the melting of sea ice. So in this section we'll just compute a quick computation and visualize the correlation between temperature and sea ice extent. So here is our temperature dataset that we have downloaded in the beginning of this training. So you can see here the main difference with the sea ice dataset is that here we have downloaded several level of depth. So we have a fourth dimension, which is here, and we've computed it to the max, which is 100 meters. So we have data up to 100 meters of depth. And we have a temperature variable with all the metadata, which is in degrees Celsius. So for this section we only use the surface temperature, so we have to select the data at depth equals 0, and we'll also perform the spatial average to have a time series instead of a 2D series. And we do the same thing for the sea ice extent. So now we have two time series, a time series of temperature over 30 years of monthly values, and a time series of sea ice extent, also monthly values over 30 years. And we will just plot one versus the other in a scatter plot. So this is what we're doing in this cell. And as you can see, so the distribution of those points, so the x-axis is sea ice extent and the y-axis is temperature. And we can see that there is a strong inverse correlation with minus 0.97 Pearson correlation coefficient, which shows a very strong inverse correlation, and it's also very visualized here because you can clearly see that there is a line here, a diagonal line, which is well centered around which the data is centered. And you can also see another thing, because we have colored the depending on the year. So the blue dots are the most ancient, and the pink dots are for the most recent years. And you can see here, so where the sea ice extent is maximum, so this is winter. Well, the area is maximum here for the old years, so during the 1990s, and we have a smaller value of winter sea ice extent for most recent years. So here it's near 2020. And the same thing goes for the minimum of sea ice extent. Those happened for the most recent years, and not necessarily for the years located in the 1990s. And so, while also showing the correlation between Arctic sea ice and temperature, this also shows that there is a gradual decrease over the years of the sea ice extent globally. Now, in this final section, we'll try to look at the potential impact of the sea ice melting, which is a change in the ocean heat content. So one of the main effects that is provoked by the Arctic sea ice is the albedo effect. Because of course, when the ocean is covered by sea ice, it absorbs much less light from the sun, and therefore much less temperature than with sea ice, than when there is no sea ice. So of course, the melting of sea ice leads to an increased absorption. And we will try to take a look at this deep within the ocean layers. So this is why here our depth dimension will be important. So here is a reminder of the dataset that we have downloaded with temperature. And what we're going to do, we're going to cut a slice in the ocean and see what happens with temperature at several depth levels. When there is sea ice, and gradually moving on with time when there is less and less sea ice. So here we define our slice, our area of interest. So we're going to have a constant latitude and longitude range to define the slice. So as you can see now, we only have depth and longitude dimensions, and of course time. And to show you where we'll be studying our data, we will plot this on this map. So basically our slice is here. And if you remember our plot of special trends of sea ice extent, this is an area where the sea ice extent is decreasing very, very rapidly. More than 30% per decade for each pixel in sea ice concentration. So let's plot a slice at a recent date, for example August 2021, to see what it can look like. So here is our heat profile. So you have on the y-axis depth and longitudes on the x-axis, and the colors are defined according to the temperature. And you can see here that we have strong temperatures at the surface. This is normal, but it penetrates quite deep within the ocean layers. So this is for a recent date, and now we're going to compute it for several dates and see how it evolves during the last 30 years. So as you can see here, we're doing this for every year. And we're doing actually the same plot for each for the 30 years of data, and saving them in this folder here. So they've already all been processed. And we're going to use these libraries to gather these images into a single GIF file in order to have an animation. And this is what we do here. and we can see the evolution of the heat profile of this slice. And you can see that as we go further further through the most recent years, the areas for which we have a deep penetration of temperature are more and more frequent, which shows that well, this area is more and more frequently not covered by sea ice. And this clearly shows well, the impact of the melting of sea ice, because of course this penetration of heat has implications for currents, for the life of the marine wildlife, for example, which may not be used to such temperatures. So, for example, and also can have an impact of the migration routes of certain species. So yes, this is quite a significant impact of the melting of sea ice. So now we are reaching the end of our training. Here are a few exercises to go further if you want to play more with the notebook. So there are a few quite easy beginner exercises and a few perhaps more advanced exercises. So basically what you can do is try to perform similar analysis on other areas or using other variables from the dataset that we have not shown here. So feel free to explore. This is what the notebook is meant for. And of course, if you have any other questions, don't hesitate to contact the service desk of Copernicus. And all in all, I hope that you have enjoyed this training, and I've been happy to present it to you. So thank you very much for your attention, and goodbye.